Welcome to the afternoon session. So our first talk in the afternoon is going to be enhancing the MPI Collective Communication Performance using iMEX. And this will be presented by Dr. An. She received her PhD degree in the School of Computing from Korea Advanced Institute of Science and Technology. She's currently a senior researcher at ETRI. Her research interests include distributed and parallel computing, AI, and high performance computing. Please.
Okay. Hi, I'm HooYoung from the Supercomputing System Research Section at ETRI in South Korea. I will present the research on enhancing the MPI Collective Communication Performance utilizing iMEX, which stands for Intelligent Memory Expander. And this is the joint research project between ETRI and OSU. This presentation covers the motivation and program definition, project goals, roles of ETRI and OSU, our approach, roadmap, and conclusion. Large-scale data-intensive applications in HPC and AI require distributed processing in a multi-node environment. At this time, there is a large and complex communication between nodes, and providing sufficient memory capacity for these applications is one of the necessary conditions for performance improvement. For example, LLM applications perform distributed training because the huge size of models and data, and the all-gather and reduce-scatter are used as the main collective communications. And as the data and model size increases, the collective communication message size also increases. However, all-gather and reduce-scatter have problems with increasing latency for large message size. And these graphs shows our experimental results on ETRI schema-based for computing nodes. And we conducted OSU micro benchmark. And we can see that as the message size increases, the communication latency of the traditional all-gather also increases. Specifically, the all-gather latency increased significantly for large messages. And we believe that we could address this issue by utilizing the CXL interconnect and the CXL shared memory pool device in a single leg, which provide faster communication latency compared to the traditional multi-node interconnect, such as Ethernet and InfiniBand. Because the memory access latency for CXL attached file memory across nodes can be as same as the latency for the CXL switched memory within a single node, which is about 3 times faster than the latency of the InfiniBand interconnect. So the goal of this study is to enhance the MPI internal collective communication performance in a multi-node environment connected via CXL. And we have two specific goals. The first goal is to utilize the CXL memory pool for the collective communication. And the second goal is to utilize the intelligent CXL switch for collective communication. And to achieve these goals, we propose intelligent memory expander. And in today's presentation, I will share our research progress on the first goal. This figure shows the key concept of iMEX. The OLEDUs is most commonly used in data-intensive applications of AI and HPC fields. In the conventional computing architecture, computing nodes are connected via the network switch. And in this architecture, the lengths in different computing nodes perform pairwise communication. So the number of communication is n squared, and the communication latency is 2 to 4 microseconds. And the MPI computation is performed on CPU of each node. So the number of computation becomes n. And the memory utilization is low because not all the system's main memory is utilized. On the other hand, in the proposed computing architecture, the computing nodes are connected via the intelligent CXL switch. In this architecture, the number of communication between computing nodes becomes n, and the communication latency is 300 to 400 nanoseconds because these computing nodes are connected via the CXL interconnect. And the number of the computation of MPI operations are performed in the dedicated accelerator, so the number of computation becomes 1. And the memory utilization is high because the computing nodes are equipped with less main memory than the conventional architecture. And the MPI ranks running in the different nodes utilize the CXL memory pool to compensate for the memory shortages, main memory shortage. So this table shows the roles of ETRI and OSU. The ETRI focuses on research into single leg scale CXL memory pool and intelligent CXL switch, while OSU focuses on research beyond the leg scale CXL memory pool. For the goal 1, we propose the CXL shared memory-based altogether. For this approach, we design and implement altogether utilizing the CXL shared memory pool as the communication buffer of the collective communication. And we measure the altogether latency with OSU micro benchmark for performance validation. In this proposed approach, we can expect the performance improvement by reducing the number of communications and achieving the performance gains with CXL interconnect over Ethernet or InfiniBand. So we developed 5 CXL memory APIs that are utilized for CXL shared memory-based altogether. These are the CXL memory APIs, CXL memory initialize, CXL malloc, CXL write and read and free. So MPI ranks running in different computing nodes can utilize the CXL shared memory pool device as the communication buffer for collective communication by using these APIs. So we implemented the CXL-based altogether in the altogether.c file of MPI 2.3.7. And we implemented the CXL memory manager.c in the CXL in the collective communication directory of the MPI2 and the CXL memory manager.h in the include directory. So this CXL shared memory based altogether utilize the CXL write and read for the internode IPC. For the experiments, we utilize the software emulator called Fly Simulator, which emulates the multi-node CXL shared memory pool device in QEMU. And we utilize the AMD EPIC 128 core processor and approximately 800 gigabyte main memory for the host machine. And for the guest machine, we utilize the QEMU CXL branch, and we use the Fedora 38 operating system and OSU micro benchmark. And the experimental items include the performance with increasing the number of nodes and performance increasing the process per node and the message size. And this graph shows the performance as the number of nodes increases. The results show that with 10 nodes, the maximum performance improvement was about 17 times. And with 4 nodes, the minimum performance improvement was observed. Minimum performance improvement observed was 6.6 times. And we utilized the 4 ppm in this experiment. And in this experiment, we utilized the 32 megabyte message size, which is the largest message size in the OSU micro benchmark. And this graph shows the performance as the ppm increases. The results show that with the 6 ppm, the maximum performance improvement was about 10 times. And with 1 ppm, the minimum performance improvement was observed. Minimum performance improvement observed was 1.77 times. And we utilized the number of nodes, 4 number of nodes, and 32 megabyte message size in this experiment. And this graph shows the performance as the message size increases. And for the mid-sized messages, we achieved a maximum performance improvement of about 5 times. And for large-sized messages, we achieved maximum performance improvement of about 6.6 times. And this is our roadmap. There are 3 stages in our roadmap. We aim to improve the performance of data-intensive applications in multi-node systems. In the first stage, called MPI, we developed the commercial FPGA board-based MPI, which has up to 32 gigabyte expanded memory and prototype version of accelerator. And it supports a single node connected to the host processor through PCIe. And this is the stage 2, iMEX, and we are here. In the iMEX stage, we are aiming to support multi-node system utilizing CXL interconnect. And the iMEX will accelerate the MPI collective operation using dedicated accelerator, and it will use the expanded CXL memory pool for the expanded memory capacity. In the stage 3, we will improve the scalability of iMEX. And so the multiple iMEX devices will be connected to a single CXL switch. And we will support more complex topology in this stage. So this is the conclusion. We expect to enhance the collective communication performance utilizing iMEX MPI computation accelerator. And we expect to improve the memory utilization of HPC systems by utilizing the CXL memory pool as the MPI communication buffer. And we also expect to improve the AI and HPC application performance by reducing the communication cost. And thank you for your attention. If you have any questions, feel free to ask.
Yeah, so I have a question. So based on what you described, the proposed solution is similar to what existing 6L hardware have, like memory devices, and maybe in future about the 6L switch. So how does your solution different from what 6L hardware may provide?
Oh.
Right. Thank you.
Any other questions? Yeah. Just use the mic.
Yeah, I mean, the result looks very impressive. So one thing I have is, because you emphasize use of CXL, right? And CXL is an extension of PCIe. So what specific features, the new features that you think benefit you actually explore to get your results?
Okay. The main benefit of our proposed approach is you can refer this figure because in the traditional altogether, there are pairwise communication between computing nodes and ranks, but by using this CXL shared memory pool device among multiple computing nodes, we can reduce this number of communication like this.
Reduce overall number of
Yeah. First benefit is come from by reducing the number of communication, and second benefit is we can avoid the TCP/IP network stack. So we don't use the TCP/IP stack, and we use the CXL memory read-write operations. Yeah.
shared memory by the
Yeah.
requires overall able to number of messages.
Yeah, sure.
Any other questions? Yeah. Microphone. Yeah. Push.
Yeah, so in traditional shared memory, right, on systems, traditional shared memory, like with mmap, there's a limit on how much you can pin, right? Because there's like a performance degradation when you use too much. Do you think there is something like that with like an upper limit with CXL SHMEM, or like how much memory can we use on the CXL device?
Currently, we set up the CXL memory, the capacity of CXL memory pool device as 32 gigabyte.
Yeah.
Yeah. So it's very enough for the benchmark.
So have you done any studies on like how much memory you can pin at a time and what happens when you increase it? For example, maybe pinning 16 gigabytes versus 4 gigabytes, you might see better performance with 4 gigabytes, right? Just assuming like depending on how much you use, like have you done studies like that? Just like changing the amount of memory you're using on the device.
I think now in this experiment, the CXL memory capacity was enough. So when we if we increase the memory capacity, but the result will be similar with this result. However, now recently I conduct more experiment regarding the number of nodes and message size and PPN. So when I use more computing node and more PPN, I will increase the capacity of CXL memory pool. Then that
Okay.
will be.
Okay, thank you.
Thank you.
Any other questions? Okay, if not, let's give a thanks to